All right, in the previous tutorial, we talked about converting from degrees to radians. So we've walked through the unit circle, we've filled in degrees before, we've found the coordinates around the unit circle. The only thing different now is filling in the radians. So I'm going to go back through filling in all those pieces, as well as the additional step of filling in the radians. All right, as well as the best way, the fastest way in order to get these values in. The more you can use them, the more you can commit them to memory, the faster your evaluating would be in calculus. So first thing is to fill in the degrees. So this is 0 degrees. And then we got to remember that the angles come from the special right triangles of 30, 60, 90, and 45, 45, 90. So we have 30 degrees, 45 degrees, 60 degrees, 90 degrees. All right. And then you're just repeating that in each quadrant. So the distance from 90 to 60 over here, right, that's a 30-degree difference, right? So there's going to be a 30-degree difference here, so this is 120. All right, there's a 15-degree difference between 60 and 45, and 45 and 30, so there's going to be a 15-degree difference. So we have 135, 150, and then again a 30-degree difference. So it's like adding 30, adding 30, adding 15, adding 15, adding 30, adding 30, adding 15. Right, so add 30, that's 210. Add 15, that's 225. Add 15, it's 240. Add 30, it's 270. Add 30, it's 300. And then 315, 330, and it ends at 360. All right, so for radians, you don't want to go around and convert every single one of these individually. All right, so I'd rather use proportional reasoning again. If I can just find, most of these angles are multiples of 30 degrees, right? And the other ones are multiples of 45 degrees. So if I can just convert 30 degrees and 45 degrees, I should be fine. So 30 degrees, right? I can either use the proportional reasoning or, and this is safer because it works with all methods, is dimensional analysis is, all right, there's 180 degrees in every pi. All right, 30 degrees goes into 186 times. All right, so this would be 1/6 pi. Another way to show it, right? 30 degrees out of 360. This is a 12th of a circle. A full circle in radians is 2 pi, so 2 pi over 12 is also 1/6. The same thing with 45 degrees. 45 times pi over 180. 45 goes into 180 4 times, so it's pi over 4. Similarly, if I do 45 out of 360, that is 1/8 of a full circle. So that'd be 1/8 of 2 pi, which is also pi over 4. And I'm going to just denote that in the top right. So 30 degrees is pi over 6. 45 degrees is pi over 4. All right, and then we can just add fractions, and I'll go slow. So I'll reduce later. So if I'm filling these radians in, right, so we got 0, pi over 6, or 1/6. I'd skip over. I'm going multiples of 30 degrees, so 6 degrees would be 2 pi over 6. This would be 3 pi over 6. 4 pi, or I'm just going up by the 30-degree mark. It's going to skip over 135, because if I add another 30, it's 150, so 5 pi over 6. 6 pi over 6. 7 pi over 6. Skip over. 8 pi over 6. 9 pi over 6. 10 pi over 6. 11 pi over 6. All right, now a lot of these fractions do reduce because they're even or they're a multiple of 3. So I can go back now. Now originally, usually I can simplify mentally, but I wanted you to see that I'm just counting up by ones. 1/6, 2/6, 3/6. And now we can reduce. So 2 pi over 6, well, that's the same thing as a third. Oops. All right, so that would just be pi over 3 or 1 pi over 3. 3 over 6, that's the same thing as 1/2. So pi over 2. 4/6, oh, that will reduce to 2 pi over 3. 5 pi over 6 can't reduce. 6 over 6 is just 1. Let's see, oh, got that cleanly. 7 pi over 6 wouldn't reduce. 8 pi over 6 you can divide by 2, you get 4 over 3. 9 pi over 6 you can reduce by a factor of 3. It's going to be 3 pi over 2. Reduce by a factor of 2, you get 5 pi over 6. Do the same thing. 45 degrees, we got pi over 4. 90 degrees is 2 pi over 4. We've already got that. 3/4. 4/4. That's already pi. 5/4. 6/4. We already have that. And 7 pi over 4. Alright, so if I can just get 30 degrees and 45 degrees correct, I should be able to fill in all the radius lengths around the unit circle. All right, and I can fill in the quadrant angles. So I got 1, then 0, 0, then 1, -1, 0, 0, -1. Right, and we can again go through special right triangles, and we can, find using the Pythagorean theorem those two lengths using a 30, 60, 90 and a 45, 45, 90. But if we're trying to get faster at it and we're trying to know a mnemonic to go more quickly, all right, now we know that all of these have a denominator of 2. All right, all of them have a denominator of 2. All right, I could even get rid of those quadrant angles. Even though I think those are easy, we could still use this trick on all 4 areas. All right, so if I just put a 2 under everything, let's see how this trick works. I'm also going to do my signs at the same time. All right, so a lot of times they don't use the quadrant angles, but the student pointed out to me that it actually works with the quadrant angles as well. So I can go square root 0, square root of 1, square root of 2, square root of 3, square root of 4. Then back down. Oh, screwed it up. That's why I don't like tricks. I started the wrong way. So 0, square root of 1, square root of 2, square root of 3, square root of 4, square root of 3, square root of 2, square root of 1, square root of 0, square root of 1, square root of 2, square root of 3, square root of 4, square root of 3, square root of 2, square root of 1, back to 0. All right, then I can start the other way where I start with square root of 4, square root of 3, square root of 2, square root of 1, square root of 0, square root of 1, square root of 2, square root of 3, square root of 4, square root of 3, square root of 2, square root of 1, square root of 0, square root of 1, square root of 2, square root of 3. All right, we're used to 1, 2, 3, but what's interesting is square root of 4 is just 2, and 2 over 2 is 1. Now, I would probably just fill in the quadrants at the very beginning like I did the first time. All right, square root of 0 is 0, and 0 divided by 2 is 0. All right, so all of these actually, if you just left it, if you leave it like this, it's technically correct. I mean, it could be nitpicky, and I might be a little bit annoyed as a math teacher, but technically all those values are correct. There's nothing wrong with it. All right, but we usually don't put square root of 1 over 2 because square root of 1 is 1. We just keep it a half. All right, we usually don't write square root of 4 over 2. Well, square root of 4 is 2, and 2 over 2 is 1. Just a weird way to write 1. But technically it is correct. All right, so I could go back in and make sure that these work out right. So I don't need that square root around the 1. All right, these ones, we just have -1/0. I don't need the square roots around the 1s. But you can see how that trick would make it go a little bit faster. Oh, and I missed 2 pi. All right, so those are some tricks going around the unit circle. There's also different acronyms or mnemonics, but you can just remember ASTC. This means that all are positive, sine is positive, tangent is positive, cosine's positive, and then the reciprocals would be true. So for this would be sine and cosecant. Oops, cosecant. That's ugly. Try that again. Sine and cosecant, tangent and cotangent, cosine and secant. All right, so if you need a fast way to remember what's positive, what's negative, these are just remembering the positive ones. Hopefully that helps with your endeavors in filling in the unit circle. Hopefully I didn't go too quickly. The next tutorial we'll talk about evaluating trig functions, but also allowing it to be in terms of radians. So we're going to be focusing more on radians because I've already done a tutorial in terms of evaluating them in degrees.